All right, everyone, we're back for bivariate statistics. This time we're walking through the chi-squared test. Good news is we're going to walk through this, some of the basic logic, some of what is needed in order for you to conduct this test. And then we're going to, the next step is, the next mini lecture here will be kind of walking through this in Stata. Okay, so as you recall, we've got this whole table of bivariate methods. You've also got a copy of that in the module for bivariate methods. We've talked about the t-test. We've talked about proportional reduction and error tests, phi, gamma, lambda, and the taus. There's a whole family of taus. We'll leave the f-test for next time. And today we're going to talk about that chi-squared test. Okay, so I'm just going to highlight a couple things. Again, the key function of this test is to make a comparison of observed and expected frequencies. We'll talk about that in a second. It is a test of statistical independence, and we'll get back to that too in just a minute or so. Again, discrete variables, so we're talking about nominal or ordinal, crosstabs table 2 by 2 or larger. And here, just like with the t-test, we're going to be comparing the chi-squared statistic to a critical value. Okay, I've crossed this part off right here because that's kind of a screw up on my slide, so just ignore it, just don't pay attention to this part that I'm crossing out. All right, chi-squared test is used to determine the likelihood that two variables are unrelated in the population. It is a test based on a comparison of observed cell frequencies of a joint contingency table with frequencies that would be expected under the null hypothesis, which is no relationship. Okay. If no relationship exists between the two variables in a population, we call that statistical independence. In this case, please pay attention to this part right here, because statistical independence means that the two things operate independently of each other. And what we're interested in is whether or not these two variables are in fact related to each other. Okay, so remember, this is our null hypothesis. We are trying to reject that null. When do you use a chi-squared test? Well, you need to have at least a 2 by 2 table. You need to have an independent simple random sample with each classified according to a categorical variable, nominal or ordinal, and a single simple random sample with each individual classified according to both of the two categorical variables. Translation: that means that you don't have empty cells. Okay, so you have to have at least a 2 by 2 table. You have to have categorical or discrete variables, nominal or ordinal. It doesn't really matter which you have, but they have to be nominal or ordinal or some combination. And you have to make sure that the cells are not empty, so you can actually fill spaces in each of those cells. The chi-squared statistic is a sum. This is a sum of an observed count compared to an expected count, which is squared, right? So observed count minus expected count squared, summed up, and then divided by the expected count. But wait a second, you're asking yourself, how do I get any of that information? Okay, we'll get there. Just hold on a second. I'm going to walk through an example here. Let's say that we have a hunch about a new vaccine treatment on a viral infection that suddenly hit the news. Specifically, we expect patients in a clinical trial to have differing responses to differing treatments. We have more than one vaccine treatment around, and we want to see whether or not there's some sort of impact of those different treatments, right? So our research hypothesis, or hypothesis 1 right here, is that not all of X1, X2, and X3 are independent variables. Our vaccine treatments will have equal effects on our patients. The null hypothesis, however, suggests that X1, X2, and X3 are all equal to each other. They're all going to have the same effect on patients. Remember, again, the null hypothesis states that we expect no differences among these different treatments. All right, so we've got 3 examples. My X1 in this case is a treatment that I just made up called Desilu. X2 is Habermasil. And X3, like a good scientist, I'm going to have a placebo, of course. And in this case, we have patients that don't improve and patients that improve. Okay, we've got a whole bunch of folks that have been testing this stuff out. All right, step 1, we need to get a chi-squared statistic by first getting expected counts for each cell. So in order to get an expected count for each cell, we conduct this simple process, which is multiplying the row total times the column total and dividing it by the table total. Wait, what is she talking about? Hold on, I'll show you in a second. Row total. So, row total is this right here. So this is X1, X2, X3. These are the patients that did not improve, patients that did improve. And so I'm going to get a row total by basically adding up these different numbers. So 14 plus 10 would give you 24. I could do that for each of these. 6 plus 18 would give you 24. 4 plus 20 gives you 24. I'm also going to go down those columns. So I'm going to add up all of these frequencies and get a sum of 24 here for this column, a sum of 48 for this column, and for the entire table I would go ahead and add up what we've got along these two, and I would get a total, a table total of 72. So, row 1 total, okay, row 1 total is this 24 right here, which I am going to bring right there. Whoops, sorry, that's going to be confusing. I'll clarify this in a second. Column 1 total, on the other hand, right here, that's column 1 total. So 24 times 24 divided by 72. Okay, so that's an expected count of 8 for row 1, column 1. Right? So the expectation right here for this cell, an expected count for this cell is 8. Does that make sense? We would do this for each of these. So I would do the same for row 1, column 2. In this case, my expected count is 16. For column 1, row 2, right here, my expected count is 8. For column 2, row 2, right here, my expected count is 16. For row 3, column 1, my expected count is 8. So that's this cell right here. And for this last cell right here, row 3, column 2, my expected count is 16. Okay? So what we are going to be doing, the chi-squared statistic basically takes each of those expected counts and compares it to the observed frequencies in each of those cells. Does that make sense? So we will eventually be subtracting 14 minus 8, 10 minus 16, 6 minus 8, and so on. Okay? We calculate the chi-squared statistic by doing what I just mentioned, which is we're going to take the observed count for each cell, compare it to the expected count for each of those cells, because we've got all that information now. We're going to square each of those subtractions, and then we're going to sum them all up. We're going to square each of these subtractions divided by the expected count, right here, and then we sum everything up. Okay, so and I made a mistake right here, so I'm going to clarify that. So for X1, no improvement group, so that's that first column, first row, our initial calculation here is 4.5, right? We're going to take the observed count, which was 14, subtract it from the expected count for that cell. We're going to do that subtraction, square it, and divide it by 8. Okay, so we get 36 divided by 8, which gives us 4.5. For X1, right, so column 2, row 1, we're going to get our chi-squared statistic, which is 10, and our expected count for that one should have been 16. So we're going to square that and divide it by the expected count, which was 16. Following me so far? So remember, the second number right here is the same as the denominator. Second number, same as the denominator. Second number, same as the denominator. Make sense? And we're going to be just doing that subtraction, in each case putting in the actual number we get for each row and column or each cell, comparing it to the expectation for that cell, squaring it, and dividing it by that same number, which is the expected count. We'll do this for each of the cells in our table. We'll go all the way through until we get a total. In this case, we'll sum it all up and get a total of 10.5. All right, so once we've done all that, so our chi-squared statistic in this instance is 10.500. We compare it to the critical value. Where is the critical value, you're asking? Well, this is much like the t-test that we had just talked about. And you're going to go to your book, page 347, Appendix C. You're going to find the chi-square distribution. Much like that t distribution, the first step in trying to determine what the critical value is obviously setting up your level of statistical significance. If you look at the very top of that table, it's got 0.250, 0.10, 0.05. Now we know that our typical standard level of statistical significance for us is always going to be 0.05, the 95% confidence level. So the second question, once you've figured out what column you're looking at, the second question is, what row do I look at? In order to determine that, you need to know what the degrees of freedom are. And as is the case, as I mentioned last time, degrees of freedom will depend on each different test that you conduct. In this case, the degrees of freedom is determined by a simple multiplication, wherein we compare the number of rows in the table and subtract it from 1, and the number of columns in our table and subtract it from 1. In this case, we had 3 rows, so 3 minus 1 is 2. And we had 2 columns, so 2 minus 1 is 1. So 2 times 1 is 2. 2 is our number, the number that we're interested in. That's our degrees of freedom. So if we had a ruler and kind of went down, we would go down to 2. As you see on the very far left-hand side of the table, you've got degrees of freedom numbered from 1 to 100. Our second line right there gives us our 2 degrees of freedom. So just scoot on over to the 0.05 level, and you'll find that our critical value is 5.99. Okay, so let's remember, we're comparing 5.99 to our chi-square statistics. Sorry for my terrible handwriting, which looks kind of like a young child has just written this. We are comparing that, to this number right here, which is 5.99. Again, sorry for messing up that number. So, when we have exceeded that critical value, we have shown a level of statistical significance, which means we can reject the hypothesis, the null hypothesis that we started with, which is the null hypothesis of statistical independence. Okay? So in this case, we get a nice check mark because we have just found a statistically significant difference that shows that the different vaccine treatments actually had differing effects on our patients. Hooray! We can now report this to someone and quickly manufacture a vaccine. All right. Well, that's it for today. We will return next time. The next little presentation slideshow will focus on how to do this in the lab. All right.